All right, Wiz, we've got a fun one today. We're kicking off the optimization of LLMs series, and I'm excited about this. I mean, many folks know that for 10 years as a university professor, I saw that the only people that were succeeding in a 21st century workforce were those that were learning, building, shipping, and sharing like legends. But what I don't often talk about is I actually spent 10 years kind of before that studying engineering and ultimately getting a PhD in optimization. And that actually meant something quite different in 2015 than it means today. This is something we've been talking about quite a lot. And with the advent of something like group relative policy optimization from the DeepSeek team, and as we see these emerging methods, we've covered one recently from Meta. This is something that actually is at the core of what we're doing with AI and with LLMs is optimization, right?
It is. I mean, that's it. It's just very fancy and very, very involved, but that's it. I mean, there's not much more to say.
It's not that fancy though, right? And that's the thing. I think a lot of times people read these papers, they see all these equations, they get really like, oh my God, what is this? All these crazy loss functions. I'm reading DPO, I'm trying to understand PPO and RLHF. And really, if you trace it all the way back to sort of the beginning of machine learning and deep learning, you can really see that a whole lot of this stuff hasn't really changed. That is fundamentally the goal of this series and something you identified quite a long time ago, right?
Yeah, I mean, and it's just one of those things where, you know, at the end of the day, we're trying to do the same thing as we've always been trying to do, right? We're looking at very similar landscapes as we've always looked at. We're just doing it like with a lot more compute behind it now. So we can scale things harder. But at the end of the day, it's the same stuff that we've been doing the whole time. It hasn't changed. It probably won't change. Maybe it'll change slightly in form, but I imagine we'll still have this idea, the same kind of idea. Optimization, as we'll learn, is a useful tool regardless of how we implement.
And as we try to do our best to teach the internet's best LLM concepts in code, we want to really dig into the concepts and the code behind things that you guys may have learned quite a long time ago, but that are still very relevant today. This is the crux of what we're trying to do in this series. Today we kick off. I'm excited for the discussions today, Wiz. There are things we've talked about behind the scenes for a long time now. And we're ready to start sharing some of that with you guys today. So Wiz, we'll have you back up in just a little bit. As we get into this today, guys, we'd love to have this be a dialogue. This is a bit experimental. This is something that we've not really tried to do before, but that we will continue to try to make as practical as possible. We're not going to bore you guys to death with stuff that isn't useful. So if you sort of put in the energy here, I think you're really going to get a lot out of this. So if you got questions, concerns, comments, as we're discussing, please go ahead and use the Slido link that is in the YouTube description or in the description on your viewing platform. Or while we're discussing, just jump right in. It's probably small groups for the first couple of these, and we'll see how it goes. So with that, let's go ahead and kick off. Optimization of LLMs. Welcome to the series introduction, everybody. By the end of this session, what I'd really love for you guys to walk away with is to understand the goal of what we're trying to do here, and then introduce the idea of optimizing LLMs. We're really going to take kind of a classic machine learning lens today, but we're going to connect it all the way up to the LLMs that you can pull off of the shelf. Importantly, we have to couch this as well, and we will in the goal part of this. Because optimization can mean so many different things in so many different contexts. So we need to put the proper stuff in context when we're talking about performance optimization of LLMs. The idea of a loss and a loss function to optimize towards, we will see is fundamental to the way everything works today under the hood. And we're going to follow a simple thread from classification all the way up to next token prediction. Today, it might amaze some of you how connected these ideas actually are. First, we'd like to define optimization for you. I want to bring you guys back to math class, maybe the last one you took, especially if you're more of a self-studier, which many of the folks in our community are, and I super appreciate that. You didn't miss a whole lot if you can connect the dots that we're going to walk you through in this series. We will see truly that everything is all about loss. And over the course of the series, that will not change. That's one golden thread that we'll pull on. Today, as we sort of look out at the future of where we want to go with this, we're going to do this about once a month. It's not very hypey. It's more of content that's going to stick around with us. This month, we're going to try to give you a little bit of a classic machine learning vibe. Next month, we're going to get into deep learning. You can think about multi-layer perceptrons, feed-forward neural nets, some of the components that make up the typical architectures that we see in transformers today. We're going to talk about computer vision, things like convolutional neural networks. We're going to talk about natural language processing, things like recurrent neural networks and long short-term memory networks. We'll also touch on the transformer. Obviously, we've got a lot of content on this already. Before we really triple down on the optimization schemes themselves and go quite deep on exactly how they work, this is going to get us into reinforcement learning territory, and it's hard to exactly predict how the sessions will go from there. But we invite you to join us throughout the series as we dig in. We're going to have some fun with it. We hope you do too. The goal of this series is to understand really what it means to optimize the performance of LLMs before you send them to production, okay? This is important because, of course, you can talk about all sorts of efficiency optimizations, cost optimizations, and all sorts of production optimizations. Once the LLM is put into an app, that app needs to be optimized. So we're going to stick with the models themselves. And that's why, it's important as we set out to sort of make sure this is clear, because optimization is way too meta of a word to cover everything. We want to stick to the LLMs themselves. As we think about sticking to these models, sticking to how we actually build state-of-the-art models today, we can go back to how we've always built models. And this is going to help us define the idea of optimization, because there's quite a long history that maybe not many people know unless you have actually spent years in graduate school studying this kind of thing. It's often quite common in optimization theory, classically, to think about black boxes. And it's useful today, I think, to think about LLMs as black boxes. Essentially, you put something in, it's black, you don't know what's going to come out, but you get something out. It's opaque. You can't really see exactly what's going on. It's not fully explainable AI, we might say. What we put into an LLM today is sort of a prompt, and we get out some sort of response. So one of the good things off the bat is we kind of are getting more or less a simple output. It's sort of a single output, which makes the optimization problem much easier. Now, of course, as we string things together, it gets more complicated with lots and lots of words coming out, especially of these latest models that can do reasoning and deep research and all of this stuff. But fundamentally, we put something in, we get something out. And that something has a specific target, has a specific aim. We might say what we get out, we want to be the optimum response. We want it to be good. We want it to be correct. We want it to be right. We want it to be, something that's defensible. We want it to be something that's explainable. We want something that's not toxic and not biased. So we want something that is really going to solve our customers' problems. We want to basically look at this black box as something that, in order to get the optimum out, I can kind of tweak and turn the knobs inside on this model. This, I could call it, sort of a dynamic empirical model where I'm changing knobs. I could think of it as more of a classic closed form representation of a model. But in any case, it's not the only part of the story in AI, of course. Importantly, we also have the data that we put in context, let's say, to LLMs. So we want to get the data that we put in right. We want to have the model and how it is performing in general, especially towards specific tasks we're interested in right. And we want to make sure that that final output, most of all, is as good as it can get. Now, things have become crazy, as Wiz was mentioning. The amount of compute and GPUs has really taken the world by storm, especially in the past decade. And so what we see things like no longer do we have hundreds or thousands of parameters, but even on a nano level GPT style model, we'll see 85,000 parameters. Or if we go up to even something that was created just a few years ago, like a GPT-3 size model, we're talking about 175 billion parameters. So it starts to get crazy. And I think like one of the things, this was a classic meme that I always enjoyed from back in the day. One of the things that's hard to grok here is the foundational elements and the foundational principles at play, because of the scope and scale and of how this has become what it is today. Now, if you want to go deeper into some of the ways that we actually take LLMs off the shelf, train them, do this kind of thing, things that we won't have time to talk about even when we get to the transformer, I'm happy to announce that we open sourced a course that we taught recently. I'd encourage all you guys to check that out if you're interested in going deeper down that rabbit hole right now. But I want to stick with the thread of optimization. Let's define it precisely here. I'd like to define optimization for you guys as the process of minimizing or maximizing an objective function subject to design variables, constraints, and side bounds. The way that we want to think about this is that we have to have some quantitative representation, some function, some number that we want to minimize or maximize. If we're not minimizing or maximizing, we're not optimizing. And so we can optimize any type of model that has variable inputs and computes some sort of output. Importantly, like the inputs have to affect the output. Of course, you can put unrelated, independent variables into something where it has no effect on the output. That's no fun, nor is it useful, because you won't find an optimal solution. You'll never converge on one. So we're not talking about doing stupid things. We're talking about doing useful things. And there's a process for finding the optimal solution to anything. It's quite simple. Once we design a system, this means actually the whole thing, right? It means the black box itself. It means the way we put stuff in, the way we get stuff out. What we want to do is we want to take that system and we want to define potentially better systems. Once we have the potentially better systems, we want to start testing them. And with each test, we want to learn something. We want to learn what we should test next. And it is this fundamental principle that you will see everywhere if you start looking through this optimization lens. And then all we do is we just repeat that until we get an optimal solution. We might repeat it till we converge based on a constraint that we provided, or we might just repeat it for some number of, let's say, training steps. And so the actual process here, and this is from a very famous textbook in these circles, The Introduction to Optimum Design. You'll notice that this is actually the design optimization process. It's quite simple, actually. We design the system. We identify the design variables, the cost function to be minimized, the constraints we have to satisfy. And then we collect data to describe the system. We estimate our initial design, and then we analyze it. We say, is this good? Is it right? Is it correct? Does it match the data? We're checking the constraints, making sure that we're within bounds of our design space. And if we have convergence criteria, are we done? Maybe we just have a number of training steps and we just, then we run it back. And so on. We make a change at the end and we iterate. Now, conventionally, how design was done is we essentially didn't do the important work of designing the system itself. We didn't identify the design variables. We didn't build a cost function. We didn't put the constraints together. We just simply collected some data and we were like, hey, that looks kind of like this. And maybe we could do this. And we built something and we said, does it do the job? Is it all right? Not quite. Let me iterate. Now, this is still quite useful, especially for, handcrafted things that you might be building. This is true in the world of atoms as well as bits. But obviously, it leaves something to be desired if you want to get hyper specifically good at something. And so the difference is simply that we're doing the important work of designing the system that we wish to optimize. And we've done this with transformers and LLMs. We've done this. We've identified what the architecture is. We've defined the single number that we want to minimize. We know what the constraints are with our language. And so it's important to sort of see this breadth of view, because when you see something like RLHF, for instance, and proximal policy optimization, which we'll spend much more time on in a later session, you see that we put prompts in. We're going to look and make sure that our initial model that we started with is relatively close. We don't want it to be too far away from our tuned policy model. You might consider this to be a constraint. And then we're going to reward the outputs of my model that I'm tuning. It's going to be my objective to get high rewards. So the objective function is going to drive updates to the model. And we're going to test the new candidate design, which is going to be a design with updated neural network weights through the transformer. And so when you can sort of step out a level and you can see that all of these optimization schemes are just optimization schemes, you can start to bring together a more holistic perspective when you think about LLMs, or when you think about new things that are released like GRPO and others today. Wiz, I want to bring you up for a discussion here. When we think about LLMs today, then, and I kind of alluded to this a little bit already, like what are the variables? Like, classic ML, we got features. What are the features in LLMs today? Exactly.
Exactly is fun. So there are a number of things that we care about, right? When it comes to LLMs. So, things like it's less so specifically features like you'd expect from, like, say, tabular data sets, right? Where each column is its own feature. We have a number of different ways that, say, like, language can be ordered in, different kinds of languages, different ways we can chunk the actual language, right? So this is as in, we can do word based tokenization or subword tokenization, or we can do byte pair encoding, or we can do even fancier byte pair encoding, right? We can do super byte pair encoding, where we actually allow for a composite token. So the opposite of subword. What if we had a word in a bit tokens, right? There's so that's just on the text, right? That goes into the embedding layer. When it comes to, like, when it comes to how many things do we want to care about, right? We have, like, things like our vocabulary size, which is a classic. We have things like, what is our embedding dimension? What are our internal dimensions, right? These things are largely analogous to features. There's so many different things that we can explore to either enhance the richness of the or expressiveness of the data that we have, or constrain it in some way. And again, that's just looking at things that I'm trying to put into feature category, right?
That's right. More feature-esque.
Yeah.
And of course, there's this classic idea in sort of deep learning where if you're learning and you sort of learn your way into features from maybe sort of a dense network that was untrained, but you're sort of learning the features, and there's plenty of examples you can pull up out there to see this. You're sort of saying, oh, okay, like this is working. This is true, actually. And in that case, maybe, we could say the feature level isn't necessarily the design variable, but rather the individual parameter level is kind of the thing we're actually designing, right? The thing we're actually updating based on our cost function is actually the weights within each neuron of the network itself, right? So the way that I guess the picture I want to paint here is the way that we set up our optimization here, what we call a feature, what we call a constraint, or what we just say, this is a sidebound, embedding dimension, tokenization strategy, all these things that you mentioned, right? Is like this really matters. So we can say, well, this is the optimum design. Because if we don't, as we talked about, design the system, then we're just iterating through the dark in the conventional manner rather than doing a truly optimum design process. So I don't know if you have any thoughts on that.
I would say largely, we are fumbling around in the dark still, right? Like we're definitely trying. We're definitely trying to say things like, well, we've added some flashlights and we've added some, some flares and stuff, but it is still a lot of bumbling. Like for instance, why 31 decoder stacks, right? Why 8 billion parameters? Why 405 billion parameters? Because it worked, right? And we're getting there through trial and error. We're not getting there through, we're going to design a network that has 10 billion parameters because that's somehow optimal for our use case or somehow optimal to represent what we needed to represent. We're just kind of trying. And right now what we found is more parameters is more better, right? So, keep pushing the number up as high as it'll go.
Yeah.
But it feels still like bumbling. There are lots of approaches that try to take us to somewhere real, right? So like DESI, has their neural architecture search, right? Where we go from a model and then we try to figure out, well, what's the right way to plug all these bits together, right? What is the optimal way to construct this network, as opposed to just here's a network. If we let enough compute and data at it, it'll sort itself out,
That's right. Yeah. And let's just say, okay, let's fully constrain this problem and say like, okay, the design variables are the parameters themselves. And I think this is maybe the easiest way to sort of start thinking about this. If I say my design variables are my parameters, how do I, like, in practice, make sure that I'm changing only the design variables that like really matter to get a specific output, right? Like, as we mentioned before, if you just change something that didn't matter, that's dumb. You just wasted your time, right? How do we make sure that the individual parameters of the billions of parameters that we're changing are actually useful to even be changed?
So we don't, largely, right? And I mean, this is expressed best through things like model merging, right? Something like DARE ties, right? Where we actually drop like 99% of the model weights, and we retain functionality, or through LoRA fine tuning, where we can train what is effectively less than 1% of the model weights, right? And get the desired outcome. So these strategies help us to they guide us toward what are the important parameters. Let's loosely say that, right? But most of the parameters in the system, because again, we're allowing compute and data to take the wheel here, right? So we wind up with many parameters that are functionally useless, right? That don't provide value. And then changing those parameters does nothing, as you said. And the only way that we can kind of force ourselves into a box where we change just what matters is by, doing these ridiculous things like LoRA and dare ties and these strategies that just basically say, well, just train very little of it, and that ought to be good,
That's right. That's right. And as we've seen, like, actually most of the parameters within the LLMs, especially as we get into fine tuning and we move from more of a general to more of a specific optimized version, they actually don't matter that much to do specific things. I mean, we're not trying to build AGI when we build apps. We're just trying to do stuff that really well.
That's it. It's the best, right? To be able to say all we care about, right, is like 1% of the parameters in this model, and the rest of them are just not necessary. Which means there's loads of space left for exactly what we're talking about today, right? To make this into a more well-designed optimization problem, right? There's 99% of the space, that we have to play with. So
that's right. Okay, so we're somewhere between fumbling through the dark and getting fully optimized LLMs. Fantastic. Okay, that's a great start. Let's go ahead and jump into a little bit more background before we are ready for another discussion and then the demo today. Thanks, Wiz. All right. So let's sort of go back for a minute as we think about kind of these concepts at a deeper level. Do you guys remember, math class where you're doing basically y equals mx plus b? And if you actually think back to when machine learning became more prevalent, more popular, we started to see that these kind of black boxes that we started building, they would do things like email spam, yes or no, sentiment analysis, good or bad, all the way up to kind of the large language models today that can obviously do lots of incredible things, but these are just some sort of simple sentence completion ideas. The important thing to think about is like what's going on inside all of these black boxes. Well, it's just some sort of calculation. It's some sort of function. It's a calculation that represents how inputs change. It's a calculation that represents how inputs change and then turn into outputs, right? So, I mean, fundamentally, what are we talking about? We're talking about like the mathematics of change itself. This is the OG, right? This is calculus. We could say the mathematics of change. We could say the mathematics of slope. Because remember, when we were in math class, maybe the last one some of you guys really, really took seriously or even took at all, is this problem was solved by looking at slope and essentially looking inside of our function, our black box, and figuring out exactly how, when I change the inputs, the outputs would change. And, this core idea is still the same thing we use for neural networks today. The idea of slope itself is exactly the idea of a derivative. It's exactly the idea of a gradient. And so when we ask ourselves like what's going on inside all of the black boxes, it's a calculation that represents how inputs change and turn into outputs. And we measure that change through gradients. And this fundamentally is how we optimize given a fully designed system. We have to see how output is affected with change in input. If the change is 0, it's dumb. There's no optimization because it doesn't affect the thing. And so, obviously gradient starts to get us much closer to buzzwords here in ML and AI. And I'd like to bring Wiz back up for a little discussion here, where I'd like to sort of let you explicate a minute on, like, what is the role of a gradient in an LLM exactly? Like, without being buzzwordy and just saying, oh, backprop obs, right? What are we really tracking the change of all the way through these bad boys?
Yeah, back prop obs, of course, like, so just so we can say it. So we're looking at how the LLM is or system that we're training is moving around the loss landscape. Okay, so if we can imagine like a big ol' field with hills and valleys, right? Like, this is the classic. What we care about, the gradient that we care about is like, we want to be, let's say the water's at the bottom, okay, of this terrain, below y equals whatever, there's water. We want to move towards the water the whole time, right? And so what we're tracking the change of is what that loss is related to, how our parameters are computing the next token, right? And when we update the network, what we really want to do is we want to get the next step, right? We want it to be closer to the water, not further from the water. Okay, with some caveats, But that's like to be ultra simplified about it, right? Like, that's what I would say.
Yeah, I mean, one of the questions, if these are next token prediction machines, we can say, okay, that next token, did it change based on this input that I gave? And, is that what I want? Right. And that's kind of, especially as we moved from solving, kind of simpler, we put these classification heads on and we sort of solve simpler problems, to now just the generic next token predictor is the thing you're pulling off the shelf and using. I mean, I think this gets back to the whole idea of, if you don't know what you're aiming at, you can't hit it. It's like, what's the output you want? If you can't define it, you're gonna have a really hard time even understanding what you even want your gradients to do. I mean, of course, we can talk about in general, we want to update the network so that it does better at the task. But unless you really have specified the task that you want to do, it becomes quite hard to let's say, differentiate the real role of gradients from just kind of training the network just to train the network. I mean, ideally, we want to pull models off the shelf. We want to fine tune and align them to a specific thing that we want them to do. And in that way, we can sort of think about, we're making updates to the network that are going to help us accomplish our goal.
Exactly. One of the things that we do, right, is that gradient tells us, how much does parameter A matter, right, in the scheme of this computation, right? Like, how much weight is applied to that parameter in terms of our final computation. So we know we can adjust those most important weights the most in a way that minimizes or should minimize our loss in the next step. Or not minimize, but reduce, let's say, our loss in the next step. And that's kind of the magic of, tying us back to those features, which is that, if we can figure out how a parameter impacts our loss, right? And we know what direction, we know changing it in direction A, right? So increasing it or decreasing it will either increase or reduce loss. And we can do that for all of our parameters. Then we can find the way to scoot the buggy down the hill, right? With the most attention being paid to the parameters that are most important to change, or the features as we've called them earlier in the session.
That's right. And I think, being it, like, this is what's called in sort of the field, right, sensitivity analysis, is like, how sensitive is the output to the change in input. And so if you say, well, my embedding dimension, I'm going to change it from 768 to, 1284 or whatever, right? Okay. Did my output change? Okay. If it didn't, then it's actually pretty insensitive to the embedding dimension for that specific task. And so I think part of the interesting thing here is like, if we don't understand what we're doing, we literally can't even say, well, which constraint, which features, which parameters should I even try? I don't even have any intuition that I can leverage. Which one should I even try? Well, I'm only trying to do a simple this or that. I don't really think the embedding dimension would, so let me rank order the next best thing to try. If you're not able to do this with your problem space, then you're not able, then you have this massive space. And yeah, you could send a little, let's say, bot around to start sniffing, little watering holes, but it's going to get trapped in one because there's just way too many, This is the idea of non-convex versus convex optimization surfaces, right? It's like, is there one bottom? If there is, it's an easy problem. So scoping, despite how much engineers might hate it and how they think of it as a product manager thing, it really does matter if you're trying to optimize the engineering solution here. So anyways, any final thoughts before we move on to the next section, Wiz?
I just want to say, like, we're always in a local minima, right? Like, we whenever we train a model, we leave it in a pit that's low, but almost certainly not the lowest, right? Like, this is the case for all of these large models. We very rarely get to what would be like literally the optimum, right? Like we just kind of get close enough that it's good. And I mean, this is one of the things I think people who aren't familiar with the space or who are less familiar with the space might be surprised by, right? Like that these models are like poorly trained for the most part. They're a lot of them are severely undertrained, right? Like we really have this. We live in this world where we've made the math huge, and we've made the scale big enough to protect us from our sins, right? But like we're really, even now today, we're really not training these models to the optimal point. We're really not. There's plenty of examples of this, but I think it's worth thinking about that. This space that Greg was learning way back, right, is still the beating heart of our industry today, and we're still not great at it.
That's right.
We haven't been great at it since the 50s, and we're not great at it in 2025.
Well, and in fact, it opens up an interesting part of this whole discussion, which is historically, this whole field was focused on models that had equations. It was focused on specific models in specific disciplines, right? So I came from a mechanical engineering background. You can talk about statics and Newton's law and F equals ma, or you could take it further and you could talk about dynamics and vibrations and vibrational analyses in a physics-based environment where it's not just ma anymore, which is m second derivative of x over t, but it's m times the acceleration, plus you've got a damping times the velocity, plus a stiffness times the position. And now you have this closed form beauty that you can take the exact derivative of, and you can know the perfect answer. And it was rooted in all of this that optimization came about. And fun fact, when I was studying under some of the old school professors that have since retired, by the way, in the age of AI, they really hated the idea of using empirical data to get these problems right because they thought it was impossible, completely impossible. And maybe they were right. I don't know. But if you don't have a closed form solution, it's hard to be exactly right. Well,
that brings up such a fun point, right? Which is, the word model, right, that we use is it is a model for something, right? And now we kind of throw it around to mean something vaguely close to the origin of the definition, right? But like when you say someone like what model are you using, you don't mean what system are you using that represents the world in some way? You know, you're like,
right.
what pile of weights are you talking about?
That's
And
right.
it's but you know, these words come from a background that they mean something very specific, and it's fun to watch us
Yeah.
drift.
That well, yeah, and you know, if we actually use the technical terminology, we had model, which meant physics-based, exact equation, Einstein, Newton, these guys. Okay, it's right. We see the moon and it's correct, whatever. And then we talked about surrogate models, which I mean, you know, you can think about a surrogate mother. You can think about it's not quite the model. We don't make that distinction in AI, and we never have. So yeah, it's quite an interesting point there as well, Wiz. It's like, what do we mean by model, right? And then I know we could get down the rabbit hole a little bit too far. It's like, what's the difference between data and model? You know, and it's like, okay, let's not quite go there. Okay, we got to get to loss and the demo. We'll see you back in just a moment, Wiz. Thank you so much for your insights. All right, guys. So thanks for continuing on this journey with us. As we discussed, everything we want to think about really is loss. And loss is quite simple. It's what is lost. It's the difference between the actual, let's call it the true model value, and the predicted value. You know, we might even think of that as the surrogate value. And so what is lost in prediction, we can also think about as the prediction error. And what a loss function then does is it just tells you about the difference between the actual, the true, and the predicted, the estimated, across a whole data set. And this goes back all the way to y equals mx plus b. Maybe you guys remember mean squared error or root mean squared error or the like. You can actually, because you have that closed form model, solve it directly. You can set the error equal to 0. You can invert some matrices and you're on your way. Now, you can't do that if you don't have a closed form version of the equation. But it turns out that, you know, if you have enough data, you can do it empirically from y equals mx plus b to ChatGPT. And you can also do it as we started to see when ML came kind of up in the field with simple classifiers. This is an example of a loss surface. Wiz is going to show you this. Sepal length. Okay, you guys might remember this. This is a classic data set here. And you might ask, like, where is loss minimum in this design space? In this box I've drawn using my constraints and my design variables and my cost function, aka my loss function. And you can see, well, the bottom in this space is right there, easy. Of course, you can't visualize higher than 3D space. So if you have many variables and it's not clear exactly, that's where it gets a little bit more challenging. Again, we can optimize any model that has variable inputs and computes some output. The way we optimize it is we train it to understand what output we want. In order to train it, we have to know loss. In LLMs, you might ask, well, how do we use loss when training those? It's the same core idea, but it's a little bit more complicated at the end. We measure the distribution of potential next tokens we have, and then we move or we shift that distribution a little bit closer to the distribution of potential next tokens we want. This is, again, foundational. We can go back to the core process. We have our system. It's been fully defined. It's our next token prediction machine. We want to define a potentially better system design, and that potentially better system design might be described using the loss between what we predicted and what we actually should have had, what we know the truth was. And this idea of analyzing the system is fundamentally about computing the loss function. We might have some constraints. Depending on how we set up our optimization problem, Some of this can shift, but ultimately, we want to have this number that we can minimize or we can maximize. This is our cost function. This is our loss function. And so when we think, how do we calculate loss in something like a transformer? We use what's called cross entropy loss. And the easy way to think about this, we'll continue to dig more into these ideas in future events, is that entropy is like the unknown. It's like the unexpected. It's like, oh, wow, that's surprising. And so you might say, like, we want to minimize how much surprise we feel when we pick the class, when we pick the next token. We want to minimize the surprise by looking across distributions and assessing how different they are and actually bringing them closer together. So whether we're doing a simple classification or whether we're doing next token prediction, we're kind of doing the same thing. And we can get a look at that by looking directly into the code as we try to take our first stab at following the thread of loss, this time from machine learning to LLMs. Wiz, over to you.
Yes. Okay. So here we go. We've got a notebook. The notebook is basically going to talk about cross entropy loss through a multi-class classification problem. This is the way we're going to do it. The basic idea here is that, this is the same kind of, we're going to see this loss again, right? So keep in mind what we're doing. First of all, we're going to import some libraries, and my Chrome is going to crash, so I'm going to refresh it so it's less crashed. And then you're going to see that, look at this, an old favorite coming back to visit us in the age of LLMs. We've got some sklearn going on. We got some NumPy. What a beautiful day. Okay, so first thing we need to do is load our data set. We're going to use the Iris data set, as Greg suggested. Another just banger from the past, right? Most of you have probably seen this data set before, right? Like if you're watching this YouTube video, you've probably seen the Iris data set before. Basically, we've got some ideas about these different species of flower. We have the sepal length, the sepal width, our petal length, and our petal width. And the idea is we have to figure out which flower is which, right? That's the idea. So let's look at our data and see that, like, okay, it's probably going to be easy, right, to figure out, which flower is which. Like we can see among the classes, there's clear separation that exists along some of the features. And so, like, we should be able to nail this, right? So, spoiler alert, we can. Okay, we're going to pre-process it. We're going to do a train test split like the good old days. And then we're going to work through cross-entropy loss. So, first of all, we're also calling cross-entropy loss log loss. Now, this is going to be something that we'll spend time on again as we talk about LLMs. But the idea is that we're going to see, there's a probability that exists for each class, and that's either going to be, a probability that is closer to 0 or closer to 1. The crux being that we're going to we're going to look at where the petal is in reality, or the flower, is in reality, which is either going to be, it is part of this class or it is not part of that class. But our model is going to output some number that's going to be closer to 1 or closer to 0. And what we're going to do is we're going to get that probability for each class, and then we're going to compare it to the ground truth, right? Because the ground truth is going to be 0 for all classes but the correct class, where it will be 1. Our model probably won't output exactly 1 and 0s, but it's going to output a shape, right? And that shape is going to be kind of close. And we're going to look at that shape in a moment. The idea is what we're going to do is we're going to compare those shapes, right? We're going to say, hey, if the shape is close to right, then the model, you did a good job. We're going to look for those weights that are most sensitive, right? We're gonna look at the features to which this is most sensitive, and we're gonna reconsider how we think about those. When it's very wrong, we're gonna do the same thing, but we're gonna punish it a little bit more. Okay, so how do we calculate it? We've got a formula. You know, there's a formula, but in the actual code, it's really easy. We just write this code, and then we're good. Very cool. Okay. Next, we're going to go ahead and we're going to visualize it. You can see here that we have this pattern occur, right, when we're calculating our predicted versus loss. The idea being that as we decrease in loss, our probability go up for both classes. So for 0 and 1, easy. Okay. Then for cross-entropy loss during training, which is the actual set that we're looking at, we're going to see this absolutely beautiful graphic here, right? Which is going to show us here's how we cross-entropy loss go down, okay, and then we plateau very early. We keep doing more iterations because we love to overfit, and then we see that the model coefficients, which is going to tell us how close we are to the predicted label, go close to where they should be. This is the idea, right? So as we train the model, we get better at predicting which class should go where. Then, we're going to be able to look at this with the actual probabilities through softmax. So these are like an example of the output from our model, and then what the softmax is going to look like. Now, you'll notice that though the scores from our model, right, are quite varied, right? The actual softmax looks pretty familiar, right? It looks like basically 0, and 1, right? And if we look at all of these softmax probabilities, you'll notice that they look the same, and we can compare this distribution, right, to our actual ground truth, which is going to be basically, well, it's going to be literally 0, and 1. And then we can use that information through cross-entropy loss to see if we're doing good or not. So what does the loss surface look like? Well, like Greg said, it looks kind of like this, right? So this is the loss surface as we explore training our model. We can look around it. We can see that there exists some, optimal point, which is going to be where all of our losses together are as small as they can be. But you notice that it's this beautiful shape because we're only looking at actually 2 features here. When we look at a loss landscape that is more complex, it does not look so beautiful. But you can tell visually what's happening wherever we start. We want to scoot down until we get to here, right? We want to just scoot on down to here, and you'll notice that as long as we're scooting, right, we're always going to wind up here, right? No matter where our scooting starts, this is where we're going to wind up. And that's the beauty of a very simple problem. Obviously, not the case in reality. But in that simplified example, it is. So how do we train the model with cross-entry? Well, we just use .fit. This is just normal logistic regression. We need those logs, right? So log loss, and then away we go. We can evaluate the model and see how well we did. We can build a confusion matrix to see how well we did. We're nailing Setosa, Versicolor, and Virgincia, or Virginica, however you say this word. A little bit of confusion here, but Setosa, 10 out of 10, we're nailing it. And then we can look at the decision boundaries. As we saw already, right? We kind of know that these classes are separable, especially among different features. And so we see, yes, we don't see anything because it's crashed. I will go ahead and refresh the collab. Hopefully we can see the pretty pictures again. We can see their clear decision boundaries, right? This group is not close to this group, etc. And then finally, we can see what our actual predictions are and then what the ground truth is. So this is where we have this idea of we're going to minimize surprise, right? Like we're going to Virginica, right? This is true. It's 0.63. right? So it's this sample, which is going to be sample 5, right, is not likely to be things more than Virginica. And so the least surprising, least surprising example is going to be if the flower is Virginica, and indeed we find that that's the true label. And then lastly, we can look at the training curve, though we'll look at this very briefly. If we train model more, model gets stronger. This is the idea is as we further slide down that slope, allow for more time to slide down that landscape, we get closer and closer to just nailing it every time, right? So this is the foundation that we'll use to build off of as we go forward, and we'll revisit this loss for a much more complicated system in the future. But for now, that's the notebook, and I'll pass you guys back to Greg. But before I do, I'll ask you to hit the bell, subscribe. We're live every Wednesday. Love doing this. So do those things, and you'll see us next week. There you go. Okay, back to Greg.
All right, Wiz. I got one question after that, though, that I think is important to ask. Ooh, well, looks like Wiz just blue screened on us. All right, so one of the things I want you guys to think about, and Wiz, maybe you can let us know the right way to think about this, is are LLMs basically kind of just big classifiers? We just saw a little classifier. Is this a reasonable way to think about them?
Yeah, good enough.
I say yes.
I would say maybe it feels a little bit more than that, but we are figuring out what the next token should be out of a list of possible tokens.
Possible tokens, right?
Maybe that counts.
Maybe that counts. All right, we will continue that discussion next time. I'll just keep you up here, Wiz. In conclusion, guys, thanks for kicking off this series with us. Optimization is all about minimizing or maximizing an objective function. We learned that's the loss function for LLMs, subject to design variables, constraints, and sidebounds. We want to choose potential optimum designs, test them, make updates based on how we noticed stuff changed. Those are the gradients. And then we repeat the cycle, maybe for a number of training iterations, maybe until we converge on a specific number that we wanted. Remember, classification is kind of fundamental to LLMs, even if it's not strictly speaking a classifier. And next up, we'll go deeper into ML by going deep in deep learning. The series will continue next month in April and in subsequent months. So we've got a couple questions in the chat related to this that I want to just sort of shout out. Can we also have an extra session on audio and video? We are going to cover computer vision, and I'd like for that to open the door to multimodality because it's so important today and becoming only more important with time. Audio, I'm not sure if that's going to make it, to be honest with you. I don't think that it will, but if it becomes popular enough, we might consider adding it as sort of a tack on at the end. Okay, and with that, let's get into the Q&A. We've got a few in the Slido, Wiz, that I'd like to cover. This is obviously not the point, but it did get upvoted. Naga, how can we make LLMs faster and cheaper to run without losing their ability to generate high quality optimal responses? An important question, but I just want to caveat this with we're focusing on the performance of LLMs in a sort of accuracy way, not in a cost way. With that caveat, what say you, Wiz, to this?
Yeah, I mean,
lots of stuff.
Yeah, like this in and of itself can be looked at as a optimization problem. We have N techniques, all of which do different things. We have constraints based on hardware and what we need, latency versus whatever else. So this is in and of itself a problem that's well worth diving into. At the end of the day, what I would say is that using things like quantization is going to be like the first sledgehammer you pull out of your belt.
Yeah, for sure. And we got another sort of comment here. on compute. This is why it's often decided by the compute budget, I guess. You know, the role of compute budget is important here, but I think we're sort of imagining, I don't know, I guess a world where we have infinite compute, you know, that we could optimize anything given enough compute and or time. With some compute, we're sort of playing that game a little bit here. I'm not exactly quite sure what this question was asking.
Yeah, if we had infinite compute that operated infinitely quickly, we can model anything that exists, including our own universe.
Enclosed form. Yeah.
But yes, you know, compute budget exists, time exists. Both of these are heavy constraints on what we're capable of doing. Not what we're capable of optimizing, but how we're capable of approaching the optimization problem. And we use scaling laws because they tell us what kind of performance increase should we expect given we throw, you know, 4 times more compute at the problem, or 10 times more, or 50 or 100,000 times more compute at the problem. That's the idea. That's
what's the sensitivity
yes.
of the performance increase to additional compute, let's say.
Precisely.
Okay, so then finally, can you give an example of constraints that you think about? Let's stick to LLMs. Otherwise, it's too meta. But constraints when you're training, when you're optimizing an LLM, what constraints come to mind immediately, Wiz, for you?
Yeah, like language is a big one, right? Like that's a huge constraint, right? It has to be language.
Which one?
Yeah, which one? What tokens can exist, do exist, should exist? You know, what is the thing supposed to be doing? For instance, you can make gibberish machines very easily, right? But gibberish is not super duper. I don't know if that's specifically a constraint, but like we do want it to be natural language, regardless of which of the natural languages we're choosing. I mean, there are 1,000 constraints to consider: hardware, time. You know, what data is a big one, right? Even if we have infinite compute and it computes infinitely fast, but we only have like 3 gigabytes of data, our model is always going to only be able to represent that data perfectly. And that data is not going to be representative of all of the data, right? So this is the kind of thing that you're looking at.
Yeah. And also, right, if we just have a transformer, it's like we've got how many attention heads, how many blocks, how many, like you'd have to basically say, this is my design variable. These are the numbers I'm okay with it being between, go. And then you'd have this sort of optimization scheme testing the different ones one at a time, testing the different ones. Of course, if you have to train a whole 175 billion parameter algorithm and then sequentially train a $176 billion algorithm, maybe your optimization takes the next 10 years and maybe it's not worth doing after all. Maybe you need more constraints. So great question. Love the discussion today, guys. Hope you enjoyed it as well. Thank you for your insights, Wiz. I think we did it. Kicked it off. Yeah. Okay. Now it's time to close it out. Please like and sub, everybody. And with that, thank you for joining us for the optimization series introduction. If you haven't joined the community yet, we'd love to see you in the Discord. Start building, shipping, and sharing today. You can find me every Monday helping hold people accountable, whether you are just getting started or you're an absolute legend and building, shipping, and sharing every week. As mentioned earlier today, we just open sourced cohort 3 of LLM engineering, a $2,000 value per seat in November to December of last year to the entire community. Shout out to everybody that took that class. That allows us to give first to the rest of the community. You can engage with each session directly on AIMakerspace.io. Next week, we're going to cover DeepSeek week. They were like dropping it like it was hot during open source week. They had all these different optimizations that actually many of them have very little to do with inside the LLM, although that's not quite true. You'll see if you join us, there's a lot of more good optimization stuff to talk about next week. They open sourced a lot of the libraries they use under the hood, and we're going to take a look at each and every one of them. It'll be a bit of a whirlwind, but it should be a lot of fun. If you're ready to accelerate your journey to becoming an AI engineer, check out the AI Engineering Bootcamp Cohort 6, kicking off April 1st. LLM engineering serves as a great on-ramp, but if you really want to build, ship, and share, get that next job, start that startup, or make an impact in your enterprise, the AI Engineering Bootcamp is right for you. If you want to see what other folks have been building, shipping, and sharing, next week, we'll remind you again, but next week you can join Demo Day live as a public participant to see what Cohort 5 has produced. If you want to just tinker on your own, then you can always find all of the concepts and code for all of our YouTube live sessions directly through the Awesome AIM Index on GitHub. Drop a comment to let us know what you thought about this series intro, and if you're looking forward to the next one. We hope to see you next time in April, and certainly next week for DeepSeek Week. As always, until next time, keep building, shipping, and sharing. We'll do the same. Have a good week, everybody. See you soon.